All right. Hello, everybody. Um, this week we have Tim continuing. Oh, sorry, hang on. I've got a slight weird delay that sounded very strange to me. Okay. Right. Yep. Tim's going to continue about Ricci Solitons and giving us a classification, I guess. Well, he's got it up there for us to look at anyway. So over to you, Tim.
Yes, thanks very much, Paul. So might need to do a bit of backpedaling to explain where we're up to. The purpose of this lecture, as well as last, was a worthy goal, I think. Sorry, let me just write here. So the goal: classify three-dimensional gradient reaching. Classify three-dimensional gradient shrinking Ricci solitons. Now, this was done more or less previously, but with this theorem that's listed here, I think one can give a somewhat simpler proof of this. So we need to recall some things that we did last time. First of all, in order to sort of prove a result about how a priori non-compact Ricci solitons are compact, we need lots of good information about the asymptotic behavior of various quantities as we go far away from a certain fixed point. And last time I asked the question, which quantities do you need to study the asymptotic behavior of? And the answer basically is, well, all of them. We knocked over two of them last time. The first of these was the fact that we've got both an upper and lower bound on the potential function. So we saw that the potential function roughly grows like a quarter of a quarter times the distance between our point of interest x squared with the distance to a certain reference point. So that was one piece of asymptotic information that was quite helpful. Another piece of asymptotic information that we found that we're going to find quite useful is this particular lemma here, which tells us about how the integral of the scalar curvature behaves, especially when compared to the volume of certain sets. This set that we're particularly interested in is the set that consists of all points, so that the value of f of x is bounded by r squared on 4, where r is some parameter. And if you've seen these kinds of proofs before, the idea is that in the proof of the Mondiano Wang result, we're going to send r to infinity, use this result, and hopefully get some contradictions there. All right, so recall what we're going to be spending most of today proving is this Mondiano Wang result. If you've got a this is not in 3D, this is actually true in all dimensions. But if you've got a gradient shrinking Ricci soliton, it turns out that the sectional curvature is non-negative and the Ricci curvature is actually positive everywhere, then this has to be compact. The reason this is so important to classifying three-dimensional Ricci shrinkers is, you may recall that result that I stated early last lecture, that if you've got a three-dimensional ancient Ricci flow that's complete, then it actually has to have non-negative sectional curvature. So this is really, really useful for us if we can somehow prove this Mondiano Wang result. So this is what I'll be doing for probably most of today. Maybe we'll knock it out quicker than that. All right. So to start off with, well, let's make a remark and sort of without loss of generality assumption that we can make to simplify the proof. Remember that the gradient Ricci the gradient shrinking Ricci soliton equation is the following: that if you take the Ricci curvature and add it to the Hessian of some scalar function, the Hessian taken with respect to that same Riemannian metric, then you're supposed to get a scalar multiple of the Riemannian metric back. For shrinking solitons, we're going to insist that lambda is actually strictly positive. Now, because of the scaling invariances of this equation, it turns out that we can basically assume without loss of generality that lambda equals 1. Furthermore, you may recall that this quantity here is actually constant for a gradient shrinking Ricci soliton with lambda equals 1. But of course, you can add a constant to the function f here, and this equation is unchanged. And so what that means is that you can also add, well, if you add that same constant to this equation here, this changes, but nothing else changes, which means that you can basically assume without loss of generality that this constant is equal to 0. So these are some things that we discussed last time that I'm basically going to be assuming without further comments now. So we're assuming that lambda equals 1, and we're also going to note that the scalar curvature plus the gradient of our potential function squared is actually the same as f, and this holds everywhere on our manifold. All right, so we've got asymptotic, we've got good asymptotic properties of the function f, as well as the integral of the scalar curvature over certain sets. Now we're going to try and derive some asymptotics for the Ricci curvature itself. So really what we're interested in is, remember that we're assuming that the Ricci curvature is positive everywhere. And from that, and the fact that we're a Ricci soliton, we're going to try and not just again note that the Ricci curvature is positive. We're actually going to try and force it to be, well, we're going to try and provide a non-trivial lower bound for the Ricci curvature. So specifically what's going on here, remember the Ricci curvature can just be interpreted as a linear operator at every point on the manifold. And when we say that the Ricci curvature is positive everywhere, what we mean is that all of the eigenvalues are positive everywhere. And so at any specific point, take the smallest eigenvalue, let's call it lambda. Since we can do this at any point, we actually get a function. We can interpret lambda, the smallest Ricci eigenvalue, as a function that goes into the set of real numbers. But since we're making the assumption that all of the Ricci eigenvalues are strictly positive, of course, this is a function into the set of positive numbers. Now, maybe you're familiar with matrix algebra, maybe not, but the smallest eigenvalue function, this function here is going to be continuous, but it's not necessarily going to be smooth. Nevertheless, we're still going to try and do some calculus with this function. All right, in the situation described above, if we've got a gradient shrinking Ricci soliton, then this smallest eigenvalue function can actually be controlled from below by the inverse of the potential function itself. Specifically, there is a number between 0 and 1, so that the smallest eigenvalue is greater than or equal to this number b divided by f, at least provided you're sufficiently far away from that reference point, that reference point which we described to be the minimum of f. So remember last time, because of those asymptotics, we showed that, well, actually f has to have a global minimum. We're going to choose x0 to be that global minimum, and we're interested in what the behavior of the Ricci curvature is really far away from this minimum, and it turns out that we get this estimate here. Okay, so let's get on with the proof of this result. So usually I hate dealing with local coordinates, but it seemed appropriate in this particular context. For those familiar with the Ricci flow, you know that for seemingly all of the curvatures, you can write sort of Heat equations for how these curvatures evolve under the Ricci flow. If you're looking at how the Ricci curvature itself evolves under the Ricci flow, you get sort of this kind of thing. Now, of course, this is not a Heat equation, but I'm making the observation that I'm a gradient shrinking Ricci soliton. So even though there's no time here, well, I know how Ricci Solitons evolve under the Ricci flow. So that means I can exchange that sort of His equation for the Ricci curvature with a more elliptic version. And it turns out that the correct elliptic version is this one here. So the left-hand side is the F Laplacian of the Ricci curvature, where the F Laplacian is just your rough Laplacian minus this transportation term here. So we're kind of transporting, one can perhaps think about this as we're transporting the Ricci curvature in the direction of the steepest increase of the potential function f. On the right-hand side, however, we've only got the Ricci curvature and the Riemann curvature terms. We've got no derivatives here. Okay, so it's at this point that we're going to use the assumption that the sectional curvature is non-negative, because since the sectional curvature is negative, one can use this equation. Recall that we've defined lambda to be the smallest eigenvalue of the Ricci, to find that the F Laplacian of lambda is less than or equal to lambda. So basically, we were just able to kill this term because of our assumption of non-negative curvature. Now, of course, you know, you might pull me up here and say, well, Tim, that doesn't make any sense because you just said that this function lambda isn't even smooth. So how on earth can you just justify writing such an equation? And well, at least we can make sense of this equation in the barrier sense, is what Mondiano and Wang say in their paper. Now, exactly what does that mean? Well, I personally hadn't really come across this term before, but I imagine what it means is sort of, it solves the equation in the sense that it has the same properties that we would expect super and subharmonic functions to have, even though they're not necessarily smooth. So for example, if you've got a function whose second derivative, let's say just we're talking about a single variable now, if we've got an equation like lambda dash dash is less than or equal to 0, then, well, we don't know really what this function looks like, but if we specify what its boundary conditions are, and we sort of join those boundary conditions up with something harmonic, then the lambda function has to always be above that function. So even though I'm not entirely sure, my guess is that this is what we mean by in the barrier sense. If that's not true, you're welcome to correct me.
That pretty much should be true, but I guess it also can be interpreted to mean that there exists, say, a smooth upper barrier for lambda that satisfies equality. So let's say there's a smooth upper barrier H satisfies Laplace F H equals H.
Yep. Okay. Thanks for that.
Or maybe even with a less than, but with the inequality. But yeah. I mean, so the eigenvalue is sort of like it's variational, so it satisfies it's the infimum of the sort of the matrix acting in various directions, the quadratic form. And if you vary that smoothly, then you're going to go away from the right. Yeah, there's a smooth super solution supporting from what Matt just said. So yeah, so if you vary the directions sort of smoothly, you'll get an upper barrier for the eigenvalue, because the eigenvalue is the infimum of the quadratic form, if that makes sense.
Yeah, it makes sense. Yeah, so the idea then, I guess, basically is that, well, yeah, this equation makes sense most of the time, but you know, there are these technicalities associated with the smooth variance of these matrices that we need to be a bit careful about. But because we have this differential inequality that holds in the barrier sense, well, a lot of the good estimates that we would want solutions to such an equation have, well, we still get them. Okay, so to make use of this, what we're going to do is again look at values of x, which are quite far away from r naught. So I'm not sure if I define this here. R of x is going to be equal to the distance between x and x naught squared, I think. Okay, So this is just a computation here. We've got this estimate holding for the lambda function. Now, what we're going to do is introduce another function u, which is basically taking lambda and subtracting some copies of f, and 1 on f and 1 on f squared here. Now, this is just a computation. It involves, well, working out how what the Laplacian of 1 divided by certain functions is. It turns out that this term here sort of cancels with the things that it's supposed to in order to get this particular estimate going on here. And this holds provided we're far away from x naught. Now, why is it important to keep track of this function u? Well, before we look at that specifically, let's have a look at the infimum of this Ricci eigenvalue. It turns out that provided we're sufficiently far away, actually I think that's supposed to be a u there. I think that's what it's meant to be. So it turns out that because lambda, actually no, that is supposed to be a u, a lambda, my bad. Yeah, so provided we're sufficiently far away, we know that lambda has to be positive. Therefore, if we restrict attention to the boundary of a certain ball, it's still going to have to be positive even in the infimum. Now, this is a useful thing to keep track of, because as long as we actually make this R0 number, R0 larger if necessary, we can force u to actually be positive on this boundary as well. Now, the reason for that, well, it's because of the definition, it's because of how we defined this u function in the first place. We defined we defined u to be lambda minus a divided by f minus a times n divided by f squared. Since we're insisting that a is actually the infimum of lambda on the boundary, you can see that, well, since we know that asymptotically f is getting really, really large, that means that 1 on f and 1 on f squared are both getting really, really large. So what that means is that, well, since f is getting really, really large, provided we're far enough away, u is also going to be strictly positive on this boundary. Okay, so we've now got a function u that's strictly positive on the boundary of some ball. And it also turns out that in the limit, we don't really know what u is, but remember it's equal to something which we know is positive, minus some things which we know are going to 0. So asymptotically, what that means is that u actually has to be non-negative. But we're now in a position to apply the sort of maximum principle arguments we like playing with. We've got a function that's positive on the boundary and also asymptotically non-negative on its other boundary. And so the fact that u solves an equation like this actually implies that u has to be greater than or equal to 0. At least at least provided we're far enough away from x naught. So I guess the picture is, if we've got this x naught point here, we're looking at the boundary here. And really, really far away, we know that u is becoming positive. And we also know that it's positive here. And so that means by the maximum principle, it has to be positive all the way around here. So it's greater than or equal to 0, except possibly inside this set here. Okay, and that's basically the proof, because of course, the fact that u is greater than or equal to 0 means that lambda is greater than or equal to a on f plus an on f squared. And of course, that's precisely what we were aiming to prove. So this lemma is, well, I think it's quite remarkable, because it turns out that merely knowing that something is positive is actually enough to conclude that it's, well, it's greater than or equal to 1 on x, roughly speaking, if we think about, greater than or equal to 1 on f, and we know that f is basically sort of distance squared. So this is pretty interesting stuff here. What else can we do? So we've basically taken care of the Ricci curvature. Now we're going to try and use that information on the Ricci curvature to deal with the scalar curvature. Of course, since Ricci curvature is greater than or equal to, well, B on F, of course, the same is true for the scalar curvature. But we're hoping to do a bit better than that. We don't just want the scalar curvature to not be decaying too quickly. We actually want it to be growing. And it turns out that is the case. So it turns out that in the situation that we've just described, the scalar curvature is greater than or equal to that same number b times the logarithm of f. And I guess maybe I should remark that this is technically only true for the distance between x and x naught large. Yeah, so the proof of this, well, roughly speaking, we can think of the proof as just instead of adding this equation up to get the scalar curvature, just integrate this equation and hopefully the scalar curvature will pop out. Now, let me explain how that actually works. Turns out that if you've got a Ricci soliton, this is another fun observation, that the gradient of the scalar curvature has to be the same as twice the Ricci curvature applied to the vector gradient f. So again, remember that Ricci curvature, you know, it not only can it be interpreted as a symmetric 0-2 tensor, but it can also be interpreted as a linear operator. So if we raise the indices on this particular thing, we get a linear operator. So it spits in a vector and spits out another vector. Turns out that at any point, the gradient of the scalar curvature is twice the vector which is found by applying the gradient of f to the Ricci curvature. So this is actually a fairly standard equality for Ricci solitons. The reason this is so handy is, well, we basically just integrate that equation. Being a bit sloppy with notation there. So of course, remember that the Ricci curvature is actually greater than or equal to b on f. So what this actually tells us is that the gradient of the scalar curvature is greater than or equal to twice, the gradient of the scalar curvature, that doesn't make any sense because this isn't what we really should be doing, is integrating this in a particular direction. So what we're going to do is integrate this inequality here. The idea is that we take a particular reference point and start integrating in the direction of the gradient of f, using the fact that we already know that the Ricci curvature is bigger than b on f, because, well, when you integrate f prime divided by f, you're going to get a logarithm out, and it's basically the same sort of idea here, because we've got gradient f upstairs and f downstairs. When we integrate that, we're going to get b times the natural logarithm of f. Now, there's only one real technicality here, and that's that this direction of gradient f might not be that well defined. But this turns out not to be an issue, because remember we had that integral discussed earlier, namely that the absolute value of the gradient of f squared, that has to be the same as f minus the scalar curvature. So if we happen to be in a situation where there isn't a well-defined direction, where this guy is 0, well, that tells us that f actually has to be the same as the scalar curvature. But if s is equal, if the scalar curvature is actually equal to the value of the potential function, well, f grows faster than log of f, so that means that this is going to be true asymptotically anyway. Yes, that was right. Integrating in the direction generated by the geodesic of the gradient of f. So that's what's going on here. We managed to get asymptotic behavior sorted out for the Ricci curvature. We also got good asymptotic behavior for the scalar curvature. And we're now going to combine this with our estimates concerning the integrals of the scalar curvature to derive our contradiction. Okay, so this is the part where we actually classify. Well, this is the part where we show we have to be compact. So remember, what we're trying to show is that gradient shrinking Ricci solitons with non-negative sectional curvature and positive Ricci curvature have to be compact. We've already established that the scalar curvature has to grow like b times the logarithm of f. And we also know that asymptotically, f has to be the same as distance squared on 4. Okay, now if we assume for the sake of contradiction that we're non-compact, then we can just pick a direction. We can look at distances being large. And so in particular, we'll be able to find values of q so that the distance between q and x naught is equal to 3r on 4. Okay, artificial parameters there for the moment, but we're trying to think of r being large here. Okay, what can we do here? Let's integrate the scalar curvature. So clearly, let's integrate the scalar curvature over the ball of radius r centered at our minimum point, x naught. Clearly, if we simply shrink the size of the ball, we're going to lose value because the scalar curvature is positive. But because we have this estimate, namely that the scalar curvature is bigger than b times the logarithm of f, we can integrate that again. So when we integrate, we get this annoying log squared term here. And of course, we also get the volume there. So this is what we can get by integrating. We're now going to try and use some other information we know about the gradient shrinking Ricci solitons. So remember that we had this lemma from before that said that the integral of the scalar curvature around a set dr, that's actually controlled by n on 2 times the volume of that same set dr. Now, the set dr is not exactly, it's not exactly a ball, but it's sort of asymptotically, matches the ball precisely because we know that the function f grows like the distance squared on 4. Because remember that d of r was defined to be the set of x, so that f of x was less than or equal less than or equal to r, I think. I got that square wrong. No, it was the other way around. So that means that roughly speaking, the ball is basically the same as the set dr, provided r is actually large. And of course, the same thing holds at the end of this inequality as well. And we find that the volume of the set dr asymptotically matches the volume of the ball of radius r centered at x naught. So we're almost done. So we've got an upper bound for the integral of scalar curvature, and we've also got a lower bound for the integral of scalar curvature. So somehow that means that this guy here always has to be greater than or equal to this guy there. How do we finish this proof off? Well, one issue is that we're kind of comparing different things here. We're comparing the volume of a ball centered at Q with the volume of a ball centered at X naught. The way around this is kind of in the name. We're talking about volume comparison, and this is exactly how we can deal with this. It turns out that there is a universal constant n, well, that only depends on n, so that the volume of the ball of radius r on 4 on Q is greater than or equal to the corresponding thing, the volume of the ball of radius r centered at x naught. This is true because the Ricci curvature is greater than or equal to 0. So we're allowed to use our Bishop-Gromov volume comparison. So that tells us that actually this controls this, but somehow we also showed that this controls this multiplied by this logarithm term here. So if we send r to infinity, we're going to get a contradiction because this term here is actually growing as well. So this is actually the whole proof of that result. These kinds of estimates on the potential function, the Ricci curvature, and the scalar curvature are actually enough to tell us that gradient shrinking Ricci solitons with non-negative sectional curvature and positive Ricci curvature actually have to be compact. So that was the main meat of this talk. Now we're just going to do a bit of sort of elongated wrapping up to conclude what we've actually seen. So,
sorry, Tim, before you wrap up, can I ask a stupid question? Where
sure.
does the volume of BQ come from?
So what's going on here? We've got a ball of radius r centered at x naught, and we're picking a q, and let's say that the radius of this ball is r. What we're going to do is pick a point over here, say, let's call it q, so that the distance is 3r on 4. Now, what we're going to be doing here is we're saying that, let's see, how does this go? Sorry, I seem to have lost myself here.
I think someone has the right suggestion in the chat. Max says that the x naught in the second integral should be a q.
Yes, that makes a lot of sense.
And of course, yeah, that's the solution. Yeah.
Yes,
sorry.
We've shifted our ball up here.
Yeah, it's to contain. Yeah, I mean that's fine.
Yes, thank you for that, Max. Yeah, okay, so of course, yes, unlike what I suggested last time, we're actually integrating over this smaller ball here. And because of what we know about the scalar curvature, we're able to derive these estimates here. Cool. So that was the proof of that theorem. Now, in order to explain the larger context here, how we know that this is actually enough to classify all of these gradient shrinking Ricci solitons, well, it's helpful to go back to some well-known results, namely about the Hamilton-Ivy pinching phenomenon. So if you've got a point in a manifold, then we can think of our Riemann curvature tensor as a linear operator that goes from two forms on your tangent space back to two forms on your tangent space. Now, as I suggested before, under the Ricci flow, you can write an evolution equation for this Riemann curvature tensor. It turns out to be this. Again, there are some technicalities here sort of associated with the same sort of issues that arise when you're trying to establish short-time existence of solutions to the Ricci flow. In order to deal with short-time solutions of the Ricci flow, you need to use the de Turck trick to somehow deal with the diffeomorphism invariance. In the context of vector bundles, it turns out that the corresponding trick sort of deals with your gauge transformations. And this was the way to do this properly was known as the the Uhlenbeck trick. Anyway, once you've done that, you find this nice evolution equation for the Riemann curvature operator. It's basically a His equation plus some sort of quadratic terms here. The first of these quadratic terms is just r squared, so that's all nice. We've also got this other term here with a hash there. In general, that's a pretty complicated term, but it turns out to simplify quite well in 3 dimensions. In 3 dimensions, this term is actually going to be positive semi-definite, provided your Riemannian metric has non-negative sectional curvature. This is quite nice for us because we actually happen to be in this situation. Okay, so why is this helpful for us? Well, not only is positive sectional curvature preserved under the Ricci flow, but it turns out that positive sectional curvatures tend to dominate the negative sectional curvatures. If your Riemann curvature operator becomes unbounded, the positive sectional curvatures far outweigh the negativity of the negative sectional curvatures. So why do I bring all this up? Well, the main reason for that is because this is what allows us to sort of dimension reduce our space. So the issue is that we're assuming, so our Mondiano Wang result applies in the case that your Ricci curvature is non-negative everywhere. Hamilton's rounding theorem tells us that if actually your compact manifold has positive Ricci everywhere, then actually it has to be the sphere. So now the issue is what happens if the Ricci curvature does have an eigenvalue of 0 somewhere. What do we do? Well, I've written a theorem here. I've called this Hamilton's splitting theorem. I believe that the first time I saw this result proved was in one of Hamilton's papers when he was looking at Ricci flow on 4 manifolds. But the result is this: if you happen to be a simply connected and non-negatively curved 3-dimensional gradient shrinking Ricci soliton, and it turns out that that you've got a Ricci eigenvalue of 0 somewhere on your manifold, could be anywhere, then actually you have to split. It basically just has to be the real numbers times by some gradient shrinking Ricci soliton of a dimension less. In this case, it's the 2-dimensional stuff. So how does this go? Well, even I haven't quite got my head around this yet, but I can give you some ideas about how this goes down. Let's say that you do have found a point x0, so that's the Ricci curvature of a particular vector at that point is 0. What we're then going to do is sort of extend this vector v to a vector field on your entire manifold. And the way that works is through parallel transport. And this parallel transport is done along radial geodesics from your point x0. Provided you're connected and geodesically complete, this does actually make sense. It may not be well defined, but it does make sense because any 2 points can be connected by such a geodesic. Now, what goes on next? Well, remember, we're assuming that our Ricci curvature is non-negative, and we've actually got, and the Ricci curvature of this vector field is actually 0 at a point x0. So we've got a function that's non-negative everywhere, is actually 0 somewhere. And then I said the maximum principle implies that this function has to be 0 everywhere. That's basically the same sort of evolution equation for the Ricci curvature that we already saw. Okay, so now not only do we know that the Ricci curvature has a 0 eigenvector somewhere, we actually know that it has to have a 0 eigenvector everywhere. What happens now? Well, as far as I can tell, there are sort of 2 ways of doing this. One way is sort of with the de Rham decomposition theorem. You somehow have to split your tangent bundle according to this Ricci null vector, as well as everything that's orthogonal to that. Because this vector was a 0 of the Ricci curvature operator, it turns out that this splitting is invariant under the holonomy group, and so therefore you're able to use the de Rham decomposition theorem. Another way around this I've seen is you do the same thing where you extend your vector v to be a vector field everywhere, and then using the same sort of maximum principle arguments, you can show that the corresponding 1 form. So if you say that omega is the 1 form corresponding to the vector field v, then it turns out that this one form is actually closed. If we make the assumption that we're simply connected, then I think Poincaré's lemma can be used to conclude that actually omega has to be exact. and so therefore is generated by a potential function. And in that case, you would just split your manifold up according to lines where this potential function is constant. So, splitting theorem. So now I think we're in a position to sort of pool everything we've seen and try and use it to classify the three-dimensional gradient Ricci Solitons. So the first of these come by using the maximum principle that we just saw, because if we've got a three-dimensional gradient shrinking Ricci Soliton and it happens to split according to R and a two-dimensional gradient shrinking Ricci Soliton, then that somehow means we need to classify the 2D shrinkers. Well, this isn't actually too bad. What is really, really important here is that the scalar curvature, Ricci curvature, and Riemann curvatures are all basically the same thing. So that means if your scalar curvature is 0 anywhere, then by the maximum principle that is obeyed by the scalar curvature, it has to actually be 0 everywhere. If a two-dimensional manifold has 0 scalar curvature everywhere, it has to be Riemann flat. And of course, we know what those manifolds look like. There aren't many of them. On the other hand, if the scalar curvature is positive everywhere, then of course the same is true for the Riemann curvature. And then the Mondiano Wang result that we just proved implies that the manifold has to be compact. But of course, if we're compact and have positive curvature, then we're in a position to apply Hamilton's rounding theorem again, which tells us that we basically have to be the two-sphere, or if we're allowing our manifold to not be simply connected, we get RP2. Okay, now I think that was all we need to summarize what all of our simply connected three-dimensional gradient shrinkers are. So remember, there are basically two cases here. Well, there are lots of cases here. So that the two main cases to treat are, namely that the Ricci curvature is strictly positive everywhere, or Ricci equals 0 somewhere. If our Ricci curvature is positive everywhere, then we know that we have to be compact. That was the Mondiano Wang result we just looked at. And then, of course, Hamilton's rounding theorem can be used to conclude that we have to be the three-sphere. On the other hand, if the Ricci curvature is 0 somewhere, then we split into a 2D, into the product of a two-dimensional gradient shrinking Ricci Soliton and R, and we know what these look like. They have to be the sphere or CPN. So what that means is that the only simply connected three-dimensional gradient shrinking Ricci Solitons are the three-sphere, the shrinking cylinder, and just flat Euclidean space R3. But remember that we're not interpreting flat Euclidean space as Ricci flat, we're more interpreting it as the Gaussian shrinker. Now, of course, if you relax the assumption that these manifolds are simply connected, then you get more. I'm not exactly sure if this list is exhaustive, but if you relax the simply connected assumption, I think that you're allowed to replace S2 with RP2. And you're also allowed to replace the three-sphere with any sort of finite quotient, where quotient out by group gamma, where gamma acts freely on the three-sphere. Now, you might think you may be allowed to quotient out flat Euclidean space to get another gradient shrinking Ricci Soliton, but I don't think you can do that. And the reason for that is that, well, if you could try replacing flat Euclidean space R3 with a 3 torus, but it's not clear that that can be given a gradient shrinking Ricci Soliton structure. It's certainly a Ricci Soliton, but I don't think you can interpret that as a gradient shrinking Ricci Soliton. Oh, and yeah, I'm not exactly sure about this one, but I think the only thing you can do to the cylinder is replace it with a quotient of an involution, one that either preserves the orientation of your cylinder or reverses the orientation of your cylinder. So yeah, so maybe some more topology experts can point me in the right direction for how this list is supposed to look, but I think this is most of them. So to conclude, I think one of the great advantages of this theory that I've just discussed in these last two lectures is that not only have we classified the three-dimensional gradient shrinking Ricci Solitons, but we actually did it without assuming that our Ricci Solitons were kappa non-collapsed. If you're familiar with the Ricci flow literature, it seems that quite often sort of classifications that are done on ancient Ricci flows rely on this sort of volume non-collapsing assumption here. A few other remarks I need to make. That the proof that classifies all gradient shrinking Ricci Solitons, basically in the lecture today and last week, we did most of it, but there are two results that we black boxed a lot. The first of these was, of course, Hamilton's rounding theorem, a very classical result which says that if you've got a positively curved manifold, then it has to go to the sphere under the Ricci flow. And the other result that I put in a black box was the local pinching estimates that tell us the nice results that ancient Ricci flows have to have non-negative scalar curvature, and furthermore that three-dimensional ancient Ricci flows have to have non-negative sectional curvature. I was thinking maybe we could go through the proof of this, but it turns out we probably won't have time for that. But it's, as I said, it's a local pinching estimate. It's not a long proof, but it is quite technical. So yeah, that's all I wanted to do actually. So hopefully I've convinced you that classifying three-dimensional gradient shrinking Ricci Solitons isn't actually too bad. And yeah, I'll leave it there. Thanks for your attention.